Well, good morning, Rotary District 7770, and welcome to Conversations with Rotary Action People for Monday, May 17th. My name is Donald Hovitz, your CWRAP post, and I'm from the Chicora Rotary Club in Myrtle Beach. Running the stream today and the recording for us, so sorry for a little glitch there at the beginning, is Mary Gask, our Public Image Chair from the 5 Points Rotary Club in Columbia. And we're pleased to be joined by our guest speaker, Dr. Mike Angel, member of the Mars Rover team. Mike, we're going to get to your presentation after I read your bio here. Let me pull that up. Okay, so Mike joined Department of Chemistry and Biochemistry at University of South Carolina in 1993. He is a USC Carolina trustee professor and also holds the Fred M. Wiseman Palmetto Chair in Chemical Ecology. Angel is also a member of NASA's Mars 2020 science team and helped design the Supercam remote laser analysis instrument on the Perseverance rover. He has won several awards, fellow of the American Association for the Advancement of Science, elected fellow of the Society of Applied Spectroscopy. You really set me up here, Mike. Southern Chemist Award, twice winner of the Applied Spectroscopy William F. Meggers Award, the ACS South Carolina Chemist of the Year Award, and others. He is also honors from USC, Educational Foundation Research Award for Science, Mathematics, and Engineering, USC Mortar Board Excellence in Teaching Award, and the Michael J. Mungo Graduate Teaching Award. Would you please welcome Dr. Michael Angel?
Hello, thanks, Donald. By the way, Don, I did send you a short version of that bio. You didn't have to read all that. So that's on you.
Okay. Hey, it's a short bio on my end, so that's what I look at.
That's hilarious. Anyway, hello, everybody. Thanks for inviting me, Mary, and Donald. Thanks for hosting me. And Mary, thanks for letting me know I'm not the only person who doesn't know how to use Zoom. They had to walk me through this too when I signed up. Okay, so here's what I'm going to do. First of all, I'm a chemist. I'm a spectroscopist. That is, I use light to analyze samples. And the reason I'm on the science team for the Mars rover is that a lot of the instruments on the Mars rover use spectroscopy, and that's what I am. I'm not an expert on Mars. I don't know much about astronomy, although it's a hobby of mine. I certainly don't know a whole lot about NASA. Most of my research is, about half of it involves NASA. The other half involves actually oceanography, things funded by the National Science Foundation. So I'm not an expert on a lot of the things I'm going to show you. So I'm just giving you a heads up there. So the way I want to do this is I've got a presentation here ready. But what I want to do is, anytime I give a seminar, I like for the people I'm talking to tell me what they want to hear. So what I want you to do is, anywhere, at any time, stop me and ask me questions, and we can discuss anything I show. I don't mind at all. I don't have to get through my slides. I don't care if I do or not. If I do, fine. But if you want to go in another direction and hear more about a certain thing, I'm happy just to talk about that. So you guys just let me know what you want me to cover. Okay, so let me start my stopwatch. I was told I have 3 hours to give this presentation. Is that right?
Okay. Not afraid. I will say to the guest on here watching, this will now be the second week in a row we're going to open up the mic, but this is not a normal thing, guys.
Oh, really?
So okay. Normally they ask questions through the chat box.
All right,
so,
I don't mind being asked questions. So you guys just, if you want to know about something, just ask me.
Okay.
If I know, I'll elaborate. If I don't, I won't.
Take it away.
Okay. Now, can y'all see my slides?
You'll have to reshare your screen.
Oh. Okay.
Bottom.
I told you, I don't know how to use Zoom. Okay, let's see.
Bottom, share screen.
Share screen. Okay. Oh, yeah. Okay, that's right. All right. How's that?
Should be coming up. Takes a second.
Takes a second.
All right, now make it bigger.
Okay.
Good.
Everybody see that?
Yes.
Okay. All right, so then let's get started. So I've already used up 10 minutes. I got 20 minutes left. Okay, so what I'm going to talk about today, Mary asked me to talk about the Mars mission. And there's a lot of aspects to this mission. So I'm going to concentrate on one of them. There's actually three goals. And one of them, the main goal is to search for life on Mars. So that's what I'm going to focus on. And what I want to do is start by just taking you on a little journey here. So on July 30th, last summer, during 2020, during the worst of 2020, the Mars rover was launched from Cape Canaveral on an Atlas V rocket. The Atlas V rocket is the US's main rocket for launching things into deep space. And it's been launched 76 times since it was designed and built. And there's been 76 successes. It's the most successful launch rocket of all time. So this launch happened during COVID, and it almost did not happen because, as you guys know what happened last summer, everything got shut down, the whole country. The whole world got shut down. And we were right in the middle of doing the final development of this rover and the spacecraft and getting it to Cape Canaveral and launching it. And it was unbelievable how difficult that was. But it happened. And so the name Perseverance for this spacecraft is really appropriate, although it was selected by a young child, I think about an 11-year-old child, way before this ever happened. It turned out it was the perfect name, because the team had to persevere to make this happen. It was amazing effort. And at the last minute, see that, can you guys see my cursor? See that right there? This is the rover from the bottom. There's a little plaque there to commemorate. This was put on the rover at the very last minute, and it's basically dedicated to all the healthcare workers during the COVID crisis. Okay, so the spacecraft left. We launched it. The rocket worked perfectly. It left the Earth, headed to Mars at a speed of 7 miles per second. 7 miles per second. That's pretty fast. It still took 7 months to get to Mars. It traveled about 300 million miles. There's a lot of space between here and Mars. There's a lot of space between all the planets. I like to say that space is well named. You can't think of a better name for it. So the spacecraft entered the Martian atmosphere after 7 months at a speed of 13,000 miles per hour. It went straight in. 78 miles above the planet, it started to encounter the atmosphere of Mars. Mars has an atmosphere that makes it very difficult to land. So at Mars, from the time it hit the atmosphere at 13,000 miles per hour, 7 minutes later, it was on the ground. To put that into perspective, the space shuttle and the Soviets' Soyuz capsules, when they return to Earth from orbit, it takes about an hour. This thing was on the ground in 7 minutes. We call that the 7 minutes of terror because it is terrifying. The spacecraft is really smart. It did the landing all by itself because the communication time between Earth and Mars is way too slow for us to have any control. So once the spacecraft enters the atmosphere, it's completely on its own. It steers through the atmosphere, which is very turbulent at this point, and it landed with unprecedentedly high accuracy because of some of the technologies we developed since the last time we went to Mars that allows the spacecraft to choose its own landing site. Now, going through the atmosphere, it heated up the heat shield to about 3,800 degrees Fahrenheit. It's really hot. And that's because in slowing from 13,000 miles per hour to 900 miles per hour, there's a lot of friction from the air. Landing on Mars, by the way, is really hard. It's harder than almost any other planet. The moon is easy by comparison. There's no atmosphere on the moon. So we can use rockets to land on the moon, and there's not that much gravity. But on Mars, there's a considerable amount of gravity, about a third of the Earth's. There's just enough atmosphere that you can't simply land with a rocket. So you have to use a parachute, and then you have to use a rocket after that. So the parachute opened up and reduced the speed to about 180 miles per hour. The parachute slowed it down. At this point, the heat shield popped off. And for the first time, the rover, you can see here, this is called the aeroshell. The rover, which is in here with its legs up like this, I don't know if you can see me or not. And for the first time, the rover sees the surface of Mars. And that's really important because what it does, it uses radar and cameras. It has 23 cameras, and it locked onto the surface. And it calculated very precisely when to release this parachute so it could land in a safe area. The region of Mars we decided to land in is really hard to land in. It's full of sand dunes and rocks and cliffs. And so it's very important that this spacecraft could select its own landing site. So once it released the parachute then, the engines on the descent stage, here's what it looks like at this point. There's the rover. This part up here is called the descent stage. That has all the rocketry and things. And so the rockets then came to life about a mile above the surface. And then as it descended, Perseverance, the rover, used its radar and real-time images to measure its speed and altitude about every 28 milliseconds to pick a safe landing spot. And the last 12 seconds, something incredible happened. This is an amazing maneuver right here. The descent stage, 12 seconds to go before hitting the surface, lowered the rover on these umbilicals called bridles, these nylon ropes. It's 66 feet above the surface at this point. It lowers the rover. And the reason it does that is because if the descent stage came too close to the ground, it would kick up so much debris that it could damage the spacecraft. In fact, the last time we did this, the spacecraft was damaged anyway. So at this point, it's lowering the rover. Now you can see the three bridles here. There's communications cables here that are part of the connected to the descent stage. This is called the sky crane maneuver. It's only ever been done twice. This was the second time. We used the same maneuver to land the Curiosity rover about 10 years ago. Well, once it slowed down to about 2 miles per hour, the rover is now on the surface. The umbilicals were cut. The descent stage took off and went over and crashed some distance away. And now we're on the surface. In 7 minutes, went from 13,000 miles per hour to the surface of Mars, which is just an amazing thing to think about. Now, what I want to do here is play you a little video. This video is live from Mars. This is going to show you using live cameras what exactly I just went over in a short about 2 minutes, 2.5 minutes, if you don't mind, I'll do this. And the rover and the spacecraft had cameras on it during this descent from once it came into Mars. And these cameras were sending live video back to Earth. So we actually saw all of this and recorded all of this live. So let me show you this video and I'll talk through this.
We're starting to straighten up and fly.
This is from Mission Control.
Where the spacecraft will jettison the
this is the last 2 minutes
in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
That's a live view parachute being released.
Deployed. The navigation has confirmed that the parachute has deployed.
It's moving 1,000 miles per hour at this point.
In the velocity. Our current velocity is 480 meters per second at an altitude of about 12 kilometers from the surface of Mars.
So it's about 8 to 10 miles high. That's the heat shield. Now you're looking from below the rover camera, looking at the surface of Mars, and it just released the heat shield. It's about to come back into the field of view. There it is right there. It's falling away faster than the rover's descending because it's on a parachute.
9.5 kilometers above the surface.
And now the rover is looking for a landing site. And by the way, it has maps. It knows what it's looking for. It has very detailed maps of this surface. So it's not just randomly picking a site. It's picking a site that we pre-selected. And that landing site.
Filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has
we're going to land right there
on the ground. Current velocity is about 100 meters per second. 6.6 kilometers above the surface. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
Still on the parachute.
OBS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
The engines have now come on. The parachute's about to be released.
Back shell set.
Current velocity
Saw that
is
flash. You could actually
83
see
meters
that.
per second at about 2.6 kilometers from the surface of Mars.
That's the
With
delta.
confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
Here in safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of
Now
Mars.
it's going to get very interesting.
We have started our constant velocity
See
accordion,
the
which
dust?
means we are conducting the sky crane,
Watch these cameras on the left.
about to conduct the sky crane maneuver. Sky
This
crane
is
maneuver
live.
has started, about 20 meters off the surface.
There's the rover.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
So this is mission control in JPL. And those of us who couldn't be there because of COVID watched all of this, of course, remotely like we are right now on NASA's, one of NASA's servers, JPL servers. So that's the first time ever that we've been able to send back live video of a landing on another planet. So welcome to Mars. How much do you guys know about Mars? Most people know that it's called the red planet, right? It's red because it's rusty. Mars is covered with dust and soil that's basically iron oxide, which is rust. And so it has this red appearance. If you're sitting on Mars, everything looks red, and so does the sky. It looks red because it has a lot of dust in it. Well, Mars, Mars is about a third the size of the Earth. No, I'm sorry, about 2/3 the size of the Earth. So it's actually very small. It's the fourth planet from the sun. It's one of the closest planets to the Earth. When it's its closest approach, it's only 35 million miles away from us, 34 million. That's very, very close. Venus is a little bit closer, but not by very much. And because Mars is so close to us, it's really easy for us to get there. Comparatively, it only takes 7 months. So comparatively, it's easy to go to Mars. And it turns out there's a window. Every 2 years, Mars and Earth orbit allows a very close approach for the two planets. And that's when we launch. So we can only go to Mars every 2 years. And that's why it was so important last summer to launch when we did, because if we had not launched, it would have taken 2 more years, and that would have cost enormous amounts of money, among other things. So here we are on Mars. Mars is very dry. It's got an atmosphere that's mostly carbon dioxide, CO2. But it's only about 1% of Earth's atmosphere. So the temperatures on Mars are extreme. The average temperature is about minus 81 degrees. But it wouldn't require much for an astronaut or a person to stand on Mars and to survive. It's really not that as hostile as you might seem. It's like some of the worst parts of Antarctica on steroids, I guess. Very cold desert. Okay, so now let me get into the mission a little bit. So here's Perseverance. This is an artist rendition. I'll show some pictures of it later. This is a rover. It's very much like the Curiosity rover that we put on Mars 10 years ago. But it looks the same, but it's actually quite different. It's a lot bigger, a lot heavier. There's a lot more sophisticated instruments on it. The rover, like all planetary spacecraft, was built at JPL. On the left here is JPL Jet Propulsion Laboratory. JPL is just outside Pasadena, California, beautiful location. And the Perseverance was built there. The instruments, however, there's 7 instruments on the rover. The instruments were built all over the world. NASA and JPL doesn't typically build the instruments that go on the spacecraft. They're built by other people. Quickly, the instruments that are on this rover include, we'll start down at the bottom here, MOXIE, which is pretty cool. MOXIE is a little device that makes oxygen. It takes the carbon dioxide in the atmosphere of Mars and makes oxygen out of it that we hope one day we can use for astronauts to breathe and to make fuel for spacecraft. REMFAX back here is basically a subsurface radar. This allows us to look under the ground, under the surface, about 30 feet deep. so we can see what's happening in the geologically below the surface. There's Mastcam. You know, when you see on the news or on these documentaries, you see all these beautiful pictures of Mars. Most of those come from Mastcam. This is a couple of cameras that are stereoscopic, and they provide these beautiful images. Supercam is up on this mast. Supercam is a laser analyzer. It actually makes 5 different measurements. My expertise is with Supercam. I helped design that instrument. That's why I'm on the mission. Meta is a weather station, and Sherlock is another laser spectrometer for analyzing the rocks on Mars. And then Pixel is an X-ray device that also allows us to analyze rocks on Mars. These 2 instruments are out on this arm. This arm can reach out about a meter, maybe a meter and a half, and touch the surface for doing analysis. Also on the rover, there's a helicopter called Ingenuity. The power, what makes a mission like this possible, this is a really large spacecraft. And what makes, what makes it possible for us to send a spacecraft this large out to the planets is the power supply. Plutonium. Plutonium heat source is used to power this rover, and plutonium is used to power most of our interplanetary spacecraft. And by the way, the total power available from this power supply is only 100 watts. If anybody's old enough like me to remember what a 100-watt light bulb is, what it used to be, that's how much power powers this entire thing. So keeping track of how much power is being used at any given time is a major part of running this thing every day. Here's a picture of the sister to a Curiosity. This is called Maggie behind me. Just to give you an idea how big this thing is, it weighs about a ton. This is the picture that I took two years ago when I was at JPL. And this shows the building of the spacecraft. Here's the Cruz stage that I showed you in the pictures I showed earlier. Here's the reentry module right here. The rover would be inside of this reentry module. It's also called the aeroshell. The heat shield is down here. And so this in 2019, in April, almost 2 years ago, shows this being built. And look behind us over here where this worker is. This is the rover in its first stages of being built 2 years ago. So part of being on the science team involved trips to JPL, you know, for various reasons, for meetings and things, but it also involved training. We did some field trips out into the desert. This is me. I like my hat. It's a great hat. This is me in the desert in Mojave, a place called Owl Canyon Rainbow Basin. And this is one of our field training exercises, again, about 2 years ago. This is Ken Farley. Ken is the head of the science mission. He's in charge of this whole thing. He's my boss when I'm working on this mission. So I learned a lot of geology. Actually, I didn't learn much geology on these trips. I learned 2 words. I learned syncline. See that right there? That's a syncline. Don't ask me what that means. I don't really know. I learned another word. When I was out here on this trip, I was walking with Ken going down one of these slopes, and I slipped on loose rocks and fell about 20 feet. And I got all bruised up and all cut up. And the word I learned was, Ken said, oh, those loose rocks are called scree. I also learned what scree is. Let's go back to the spacecraft. Here, this shows how the spacecraft is put together, the Cruz stage on top, the aeroshell here, the descent stage, the rover, and the heat shield. Here's the final assembly about to be loaded onto getting ready to take it to Cape Canaveral. This was probably in 2020. I don't remember exactly the date on that. And you can see how the rover is actually folded up. It's kind of like origami, I guess, a little bit. It has to be folded up in order to fit in there. Now, the rover carries a lot of instruments. I already described a few of them. It has 23 cameras of all types. I mentioned Mastcam a minute ago. Mastcam are these 2 cameras here. These little squares. There's one there and there's one there. Those are stereoscopic cameras. Give you these beautiful images of Mars, but they're much more sophisticated than that. They also see in the infrared, and they can actually acquire images at many different wavelengths, and we can use that to get chemical information. On the side of Mastcam, there's a camera here and a camera here. That's called NavCam. This acquires images that lets the rover navigate. The rover is completely autonomous. That means it's all by itself on Mars. When it's doing its thing, we're not controlling it. We send it instructions, and it does everything all by itself. So it has to know where it's at. So as it's moving along, it's using NavCam to determine where it's at. There's also lots of other cameras it uses, but NavCam are the main ones. Those of us who work on the team called Perseverance Percy, by the way. So if you see me use Percy, it's referring to Perseverance. Supercam, again, is the instrument that I'm most involved in. Over here is a little animation that shows what Supercam does. It has a laser in it. In fact, it has 2 lasers. And that laser is used to shoot and target rocks and soils. And we basically can look at the light that comes back. This is a little telescope lens right here. And the light that comes back, we analyze it, and we can do chemical analysis of samples up to 10 meters away. And that allows us to extend the range of analysis by about 100-fold over just using that arm that I showed you earlier. A little bit more detail how that works. Another little animation. So here's the rover. This is an image of Mars. So let's say we select that rock right there, which we did for that particular analysis. The laser then would shoot towards that rock, would focus on it, and would form a little spark. That's supposed to be a spark. You can actually hear it. It sounds like that. When you fire the laser, when it hits the target, it blows out some of the material, forms a little plasma or a spark. And by looking at the light from that plasma, we can analyze it. And I'm not going to go into these details. We can analyze it, and we can tell the elemental composition of those rocks by looking at these are called spectra. I told you I'm a spectroscopist. This is what I do all day. I look at spectra. Okay, so let's get back to Mars. The landing site. The landing site was selected for one particular purpose. Now, first of all, let me just show you where we are. Here's Mars. This shows where other rovers have landed on Mars in the past. Here's where we landed in February 18th. We landed in this crater called Jezebel Crater. Jezebel Crater is a really special place. It used to be a lake. Sorry about that. It used to be a lake. And you can see in here, you can see the entrance channel here. This is a river coming into this, what used to be a lake. And here's the output channel here. So this was once filled with water, possibly up to 1,000 feet deep or more. Okay, so that's our target. And the reason we went there is because it's so old. It's like 3.6 to 4 billion years old. And so that's a great place to go to look for evidence of life. What better place to find evidence of life than an old lake bed, right? So welcome to Jezebel Crater. This is one of the first images rover sent back to Earth when it landed in Jezebel Crater. It couldn't be more perfect landing site. Look how flat everything is. It kind of looks like a gravel parking lot, which is perfect for a rover if you're going to land a rover on Mars. You want something flat. This has been named the Octavia Butler landing site. And again, the landing is on February 18th. So back to the delta, the Jezebel Crater. This is now an enhanced image of that crater. Here's the crater outline right here. But look right here, you can see very clearly, here's where the old river ran into here, forming this delta. The stars where we landed. By the way, for comparison, here's a delta in Alaska. So you get an idea. Obviously, this is a delta that you don't really have to, I don't have to explain this to you. You can just very clearly see this is an old river delta. And the rocks here are about 3.6 billion years old. And that's important because if you're going to look for life on Mars, you have to look at rocks which are old enough to have been there when there was life on Mars, which was about, we know, 3 to 4 billion years ago, since there was last water in that lake. Now the mission is actually 3 parts. We're in part 1. We're going to collect samples from that crater, from that delta. We're going to drive around to different sites and take samples. And then in 6 or 7 years, we're going to send another rocket to Mars, retrieve those samples and bring them back to Earth. So that's the called a sample return mission. So Mars is a cold desert, like I told you, but it was once covered with water. So here's an artist's rendition of what Mars looked like about 3.6 billion years ago. It had lots of water. And if you're going to look for life, the motto is in NASA, follow the water. Where you find water on Earth, you find life. So what are we going to look for? We're not going to look for fossils. That's what most people seem to think. We're not looking for fossils. The oldest fossils of the types shown here on Earth are less than 1 billion years old. We're going to look for things called stromatolites. That is signatures left by living organisms in the rocks. And we have examples of stromatolites. Here's a picture of one on Earth that are up to over 4 billion years old. And we know what these look like. These are signatures. These aren't the actual microorganisms themselves, but they're the evidence left behind that they were once there. So we're going to go to Jezebel because it has old rocks. And we're going to take those samples of those rocks. Here's just some pictures of stromatolites today in Australia on the left, and some of the older ones in Australia on the right. Just to give you an idea that, yeah, we know what stromatolites are, where to find them. Okay, where are we going to go? Okay, this is the crater. Once again, a little bit different view. Here's the crater rim. Here's the delta. Here's where the rover is. Here's our nominal path. We're gonna go from here over to here. That's about 2 kilometers. And we're gonna drive up onto this delta, which is old river mud. And that's where we're gonna start taking our samples. And we're gonna end up right here in the river channel itself, taking samples along the way. We'll be taking 30-some samples to be brought back to Earth. At that point, about a year has gone by, a Martian year, which is 2 Earth years. And then we expect the rover to be able to last at least 6 or 7 more years, maybe 10 years. Curiosity is 10 years old now. And so if that's the case, then we're going to continue driving along the crater rim. And we have a 6 to 7 year mission planned after that first year. Perseverance carried a helicopter, a passenger. I'm sure you all know that. Here's a picture of it on Mars. Here's a portrait of the helicopter with the rover. Here's how it was mounted on the rover. The helicopter was a last-minute addition. It really wasn't supposed to be part of this mission. So the rover was not designed to carry a helicopter. So it had to be fitted, retrofitted. And so it was retrofitted by putting it underneath the belly of the rover. You can see that right here on Mars. And so what I want to show you now is a video, very short video. Here's the helicopter. These videos were acquired by the mass cam on the rover. This is flight 5 just a few days ago. It's at about 5 meters here, I believe, above the surface. It's about 60 meters away from the rover at this point. It's going to ascend now to 10 meters. And then it's going to land. Now you look at this, you might think, well, what's the big deal? My drone can do this. Yes, I have a drone and it can do this on Earth. But on Mars, things are a little different. The atmosphere on Mars is so thin, this rover flying in the atmosphere of Mars is the equivalent of flying at 100,000 feet on the Earth. We don't have a jet that can fly 100,000 feet on the Earth. Nobody does. The closest we have is the SR-71, which could fly at 85,000 feet, maybe 90,000 feet. This helicopter is flying higher equivalent than the SR-71 jet. That took some amazing engineering. By the way, this ingenuity is very small. It only weighs about 4 pounds, but we've already got the ingenuity. The helicopter team is separate from the rover team, by the way. I'm not on that team, but they've already designed a larger rover, a helicopter, which weighs about 33 pounds for future missions, and it'll be used for scouting terrain around the rover, maybe going out, several miles away and sending back images. So the last thing I want to show you is, what do we do? People ask me this, what do you do? Like, I'm working a Mars shift tomorrow morning at 8 o'clock. I have to get up early tomorrow and be ready. What do we do during a Mars mission? How do we actually do the mission? So let me just quickly show you how this works. Well, first of all, normally the mission would be run out of mission control. You've seen this on TV. You know what this looks like. Everybody's in a big room, computers everywhere and screens, and we're monitoring the mission control in the spacecraft. Well, that all changed with COVID. Everything had to be relearned, and everybody had to learn how to do this remotely. And I'm talking about 400 and some people working remotely from all around the world to make this work. So nowadays, what we do is we work remotely from home, most of us. Very few people are actually at mission control. Here I am doing a shift one night. A lot of the shifts end up being overnight. And this is a computer that I have in front of me right now. And on the screen, I have all kinds of windows that are showing me various aspects of the rover, the satellites that are coming over, going to transmit data, when the data is going to come in. And then one of the things I do is I download the Supercam data. I do a quick analysis of it, and I post it to JPL server so everybody can see it. So that's what we do. We basically sit at our computer. We look at the data as it comes in. We analyze that data. By the way, I got to talk about this right here. This is called meeting tracker. See that red line right there? That's constantly moving from left to right. At the top is the time, is a clock. We live and die by this clock. When we're doing a shift, this red line is telling us what has to be done at what time. Because at the end of the shift, and there's no room for error here, at the end of the shift, we have to have planned the next day's instructions for the rover in time that they can be sent up to the rover, and they're radioed directly to the rover so that it receives them for the next day's activities. And the reason the time is so critical, the rover has to receive these commands just as the Earth comes up above the horizon on Mars. So just as the sun is coming up in the morning, that's when the Earth comes up on Mars, that's when we radio all of these instructions to the rover for its next day's activities. And this red line tells us when that is. So when I'm working a shift, it's kind of nerve-wracking. It's kind of stressful because I know I have to get my job done in time so that everybody can get their jobs done, so we can get these instructions up to the rover. Otherwise, we lose 2 days, as it turns out, which is very valuable time. So that's what, very briefly, what a shift looks like. Oh, my wife said, be sure to show you this. I don't know if you can hear that or not. Can you hear that?
All right, happy Cinco de Mayo, everybody. Let
me play it again. Every shift, every rover shift starts with a wake-up song. This is tradition. This has been done.
All right, happy Cinco de Mayo, everybody. Let's dive into our downlink briefing.
This is called the PUL. He's in charge of the shift. This is traditional. Ever since the early manned missions, the beginning of every day, every shift starts with a wake-up song. And so every time we start a shift, we look forward to this. There'll be a wake-up song. They're actually, for all the planetary missions, you can buy albums. Albums, I'm old. You can buy, you can download music, so you get CDs that have all these wake-up songs on them. So that's just kind of traditional. That's kind of cool. Okay, let's see. Just a couple of things to wrap this up. And, nobody's asking any questions. I hope you have some questions for me. Okay, so just a couple of cool things. I thought I'd just show some pictures to wrap this up. Here's a cool vista. This is the delta over here. The delta, again, is the mud and things that came down the river. This is where we want to go. You can see the layering in the rocks here. This is about 2 kilometers away, by the way. It looks closer because there's no atmosphere to speak of. Here's an interesting rock. You see meteorites on Mars pretty often. We're not sure that is a meteorite, but it could very well be. It looks like one. Here's another. This is called Santa Cruz. This is actually about 8 kilometers away. That's a mountain. And we've done a lot of analysis already of the rocks and things on this mountain. This is, by the way, a color enhanced image. The rocks really aren't that color. We enhance the images to show various things. So they're not really blue like that. Conspiracy theorists love our images when we post them like this because they say, oh, there's blue rocks on Mars. That means, there's aliens. No, we just do that so we can tell better what's going on. But it looks beautiful. Here's where we were several days ago. This shows you basically how we pick our targets. Okay, each one of these green lines is a target. We call these paver stones. We don't really know why they're flat and these other boulders aren't flat. That's something we've been investigating. Easter eggs, if you know what these are, this is pretty cool. There are lots of Easter eggs on Percy. NASA historically loves to hide things on their spacecraft for people to find. And if you start analyzing all of the images of the rover, you'll find there's lots of hidden messages. You probably know about the parachute message already. The parachute has an interesting design, and it's not random. It actually is encoded here in this design, dare mighty things, which is JPL's motto. Well, if you look I won't go into all of these. I'm not going to go into these at all. But just look at the images on the rover that are posted. By the way, NASA posts every single image. Every image that we ever acquire on the mission and all past missions is immediately posted to the public server. You have access to them as soon as I do. Nothing's ever hidden or held back. So anyway, you can look for these if you're interested. So right now, as of today, the rover is stopped at a location. We're headed towards the delta. And it's at the delta where we hope to find the river muds and things which we hope have preserved ancient life on Mars, where we're going to start taking our samples and bringing them back to Earth, or preparing them to be brought back to Earth. So we're headed there. Now it's going to take a while to get there, but by the time we get to the delta up in here, it'll probably be about February of next year. The rover moves, by the way, at about 0.1 mile per hour, 1/10 of a mile per hour. That's incredibly fast. You can walk 30 times faster. It's very slow doing work on Mars, very slow process. So once we get to the delta, that's when it really starts to get interesting. That's when the real science starts. That'll be this fall and around maybe by February. And hopefully by that time, you'll be hearing some amazing things coming out from the science team. If you're interested in following this, again, NASA has lots of public websites where you can follow what's going on. You can look at any of the images that have been acquired. Here's one of the links. And if you want any kind of an update, just go there. If you want to see how we take samples, I include here, you can use your cell phone right now. You can actually go to this link right here, or you can simply type in this link down here, and you can actually go watch some videos and see how we're going to actually take the samples. It's a really cool process of how we're going to do that. So with that, that's all I have. And I went a little bit over, Don. Sorry about that. Are there any questions?
Well, thank you, Juan, for you presenting, and what incredible information and photos and stuff you've been able to share with us. I don't think without you, I don't think we would ever have a chance to see or learn about this. I don't see any questions in the chat. I will say there was one comment that says, seems amazing that with a launch speed of 7 miles per second, the rocket doesn't get deflected by space debris.
Okay, that's a really good question. Everybody seems to think, you know, you guys have heard about the asteroid belt, right? And you see it in science fiction movies, like in Star Wars. Oh no, we're in the asteroid belt. We got to dodge all the asteroids. I mentioned earlier that space is well named. Space is called space for a reason. It's mostly space. The chance of hitting something on the way to Mars is infinitesimally small. There's so much space between all those little particles and things. It's not impossible though. And because it's not impossible, the way the rover's designed is, it has redundant components. So if something breaks, we have a backup. Also, all the memory and all the computer type components on the rover, they're separated out. Like all the memory that stores all the data, there's half of it on one side of the rover and the other half's on the other side of the rover, just in case something does hit it, like a micrometeorite, that we still have, you know, another half that will work. So NASA does consider that when they launch these probes, especially out to the outer planets like Jupiter, where it's much more important. But there's very little chance of hitting anything on the way to Mars. Great question, though.
And Mike, the questions are starting to come in. It might be that Mary has to finish this up today, but as I need to step away. But
okay, Donald.
Why don't you ask this? What kind of experiments are planned while the rover's on its way to the Delta?
Oh, we do experiment. Okay, great question. We're not just sitting there. We're not just sitting there. We're making measurements every single day. Today, there are measurements being made as we speak. And we're looking at the rocks. We're looking at those flat rocks. We're trying to figure out, let me tell you what kind of rocks we're looking for. They're called sedimentary rocks. Sedimentary rocks are formed in rivers and lakes and the ocean, anywhere there's water. And it's basically mud and sand that over time, over millions of years, gets compressed to form rocks. And we know on the Earth that sedimentary rocks is where you find fossils and stromatolites and things like that. So we're looking for those. We're unpacking the instruments. It's very slow to work on Mars. We're still unpacking the instruments. We haven't unpacked the samples, the drills we have, the abrasion tools. Some of the scientific instruments are still being unpacked. That is, we turn them on and test them and we calibrate them. So we're studying the geology around where we are now. Even though we're not at the Delta, you know, one of the big questions is, how old is this crater? We think it's 3.6 billion years old, but we need, you know, we need to confirm that. So we're looking for rocks that can tell us how old the Delta is. We're doing a lot of things. We're flying the helicopter. The first month was solely dedicated to the helicopter. It's now done its mission, so now we're doing our own. So yeah, we're really busy measuring what's around us. We're also making maps. There's an orbiter which gives us maps of the area. A satellite is orbiting Mars, right, with cameras, and it actually gives us images of the region around us that with the resolution. Well, we can see a small car, maybe even a really, really small car from orbit. And so we're using the rover's cameras to fill in those gaps and to make it's called a mesh Basically, it's just a detailed three-dimensional image of what's around us so that the rover can navigate. So we're busy making measurements, but we're also busy just unpacking and calibrating all the tools that we're going to need once we get to the delta. We might even take a sample or two in this area before we get to the delta. So yeah, we're pretty busy. Great question.
Mike, there's another question there from Paul Walter. He says he came late. You may have said it, but can the rover repair itself? Or what happens if something occurs with the rover? Does it have its own pit crew?
Yeah, that's a really good question. This thing is well built. The Curiosity, landed about 10 years ago. And it's kind of like this rover. This rover is much more sophisticated. It's already lasted 10 years and its wheels are falling apart. Things are breaking down. Things will slowly break down. They just will. But this thing is made out of titanium and aircraft grade aluminum, and it's made really well. The engineers who build these things are geniuses. It's unbelievable what this thing can take. This rover is, by the way, this rover can be tilted at 45 degrees in any direction and it won't tip over. It can climb a 30-degree incline. It can climb over rocks that are 15 inches high. So the short answer is, I guess it's too late to give a short answer, but it's just well constructed. There are lots of backups in here. Like I've already mentioned, the memory backups. There are a lot of redundant things on the rover. There's lots of, oh yeah, you can see them here. See that right there? That's one of the antennas. There are several antennas. The worst thing that could happen is lose communication with the rover. So there's at least 3 antennas I'm aware of that can talk to satellites in orbit around Mars and can also talk directly back to Earth. The rover can talk to the Earth directly without even going through a satellite. So there's lots of redundancy built in here too. I can't think of any other examples right offhand. Well, it's got 6 wheels. There's redundancy right there. You might ask, why does it have 6 wheels? Well, we lost one on Curiosity. It's good to have backup wheels. So there's lots of redundancy, but it's just really, really well built.
Okay, I have another question for you. What keeps the team up at night? What is the greatest risk or concern the team has about completing the mission?
Okay, the clock. That is, and by the way, the clock changes every day because the time on Mars and the time on Earth aren't synchronized. And so the time changes, like what time is it here now? Noon, let's say. Well, on Mars, let's say it's noon on Mars. But in a couple of days, when it's noon on Earth, it won't be noon on Mars. So the schedule shifts every single day. And what drives us is being able to send the rover its instructions every day when the Earth comes up on Mars, every morning for the rover. And that means we have to get the data, and that can sometimes be a problem. We have to analyze the data, quickly analyze it, and decide, did we get what we want? Based on what we got, then what are we going to do tomorrow? By the way, we call it to sol. The sol means sun, and we don't call things day on Mars. We call it sol. So today would be to sol, tomorrow is to sol. So it's that, getting the rover its instructions it needs for the next day's activities is what drives everything. The detailed analysis comes later. I mean, detailed analysis can take years and years and years, but we have to quickly analyze the data every day so we know what to do tomorrow, so we don't waste time. This rover is a national asset. It costs $2 billion. We don't want to waste any time on Mars. We want to be sure that we get everything we can possibly get out of this mission. And so this team, you can't believe how hard the science team and the teams on any planetary mission, you can't believe how hard they work. They work night and day, 24/7. They stay up all night. It's routine to be sure that no opportunity is missed to get science out of this thing.
Okay, how much power does the solar add? Another question.
Solar. There's no solar on the rover. It's strictly, it's a plutonium heat source. It uses, it's back here, back in the back. This picture doesn't really show it to us. See that right back there? There's a little capsule back there that has about 8 pounds of plutonium dioxide in it. And it's plutonium-238. We can't explode. That's 239. This is an isotope of plutonium that we make. By the way, the US has the only supply of this. It supplies heat naturally, and it's surrounded by thermocouples. Thermocouples take heat and convert it to electricity. And this thing is constantly producing about 100 watts of power. Again, that's like 100-watt light bulbs, not very much, But if you manage it correctly, it's enough. And so it supplies all the power. Now, doing the driving takes about 100 watts just to drive the rover. And so the way we get around this problem, having enough power, is there's some really large batteries on the rover. And at nighttime, when the rover's not doing, most of the activities are in the daytime, the plutonium power source charges the batteries. So it can run on batteries all day long. So there's enough power. So there's about, I forget, a day's worth of power in the batteries for most things.
I have two more questions for you. One is, when will man live on Mars? What's a projection on that?
Yeah, that's controversial. That's very controversial. Okay, I'll get in trouble, I guess, saying this. I'm not big on manned missions. You know, we can do a lot of things with robots, and it's a whole lot cheaper and a whole lot safer. But eventually we are going to go to Mars. If nothing else, Elon Musk is going to see to it that we do. He's going to see to it that we do, and other private companies. And that's great. How long is it going to be? Who knows? Elon Musk says it can be in the next 10 years. He's probably right. He's done some amazing things. The main issue, by the way, of sending an astronaut to Mars is not living on Mars, it's getting to Mars. There's a lot of radiation in space. And so you have to, and so being exposed to this radiation is not good for your health. It's one of the main problems we have on the space station for long duration missions is exposure to cosmic radiation. So the spacecraft has to be shielded really well, which means it has to be really big. Once you get to Mars, it's actually not that hard.
Okay, and one last question. How much political disagreement do you get about spending so much on this research?
I'm not involved in politics. I have no idea.
No idea.
Yeah, I mean, I actually have an idea and I have an opinion. But, you know, $2 billion for a mission like this compared to any other national expenditure is extremely small. It's unbelievably small. And we're talking about, you know, this is spread over 10 years or more. It took 7 years, by the way, no, more like 17 years, 20 years. It took 7 years to build the thing. It's going to have a mission lifetime of 10 years probably. So we're talking about spending $2 billion over 17 years. And what we get out of these space missions is, there's so many things we get out of the space mission. I know it's very controversial, but a lot of the medical technology we have, the drug development, you probably don't know the connections there, but there's drug development that have happened because of our technology we developed in space missions, the coronavirus vaccines, for example. So what we get from these missions, just the technology, is just invaluable. You know, no matter how else you look at it. I mean, $2 billion is really a drop in the bucket for what we get back. And there's another aspect of this too, and that is that there's a lot of aspects, but one of them is, I mean, do we want to give up being the leader in technology in the world to other countries? China's right on our heels. They just landed a rover. They're the only other country who's landed a rover on Mars, except for the US. They're right on our heels technologically. Do we want to stay ahead of them? Do we want to stay ahead of other countries? You know, there's different opinions on that. You have to use your own judgment on that. Anyway, there's a lot. I don't see $2 billion as being much of an expenditure for what we get out of this. Now, I am biased. There's no question. I'm biased.
Okay. I think that's all the questions that we have, Mike.
Okay.
Cannot thank you enough. This has been so informative. And we appreciate your coming on here and sharing this with us. I can't wait to take it home and show it to some family members. It's a great thing.
Appreciate it. It was fun.
Well, thank you for all that you do. If I could ask you to stop screen sharing so that I can get us back to a regular, there you go. That's perfect. Okay. Thank you very much. By the way, you're going to have somebody else contacting you from another Rotary Club, probably wanting you to come in person and do a talk for them. So just thought I'd pass that on to you.
It's about time to start doing things in person again, I guess.
Yes, it is. Getting close to it. So thank you so much. A few announcements. We have Be a Vibrant Club training coming up this Friday. Foundation is from 9 to 11, and public images 145 to 345. You can find out how to get on by going to DACDB, and it'll give you the link for that. Our speaker next week is somebody that Mike knows. It's Brian Gentry. He's with the College of Arts and Science, and he is going to talk about a survivor of Hiroshima atomic bomb who later started a movement for people that were involved in that. So should be pretty interesting. If you'll join us next Monday at 11 o'clock. And then on Monday, May 31st, there's no meeting. It's a holiday, so you'll be able to enjoy a long weekend. And in lieu of time, we're going to skip everything else. Thank you all very much for joining us. This was so informative. Thank you again, Mike. And we will see you next Monday. That's a wrap.